Okay, we are on day 2 of optimization, and today we're going to look at volume and surface area problems. So if you're following along in your notes packet, this is example number 4, and the story goes, a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So the first thing that we are going to do is we're going to sketch a picture of this open box. So I'm going to draw a rectangular figure, and the one thing they tell us is that it is actually an open box, which means it does not have a top. And they tell us that it has a square base. So with any rectangular prism, we usually have 3 dimensions: length, width, and height, but because the base is square, we'll call them both the same thing. So instead of length and width, I'll use width and width, and then we'll call this the height. And with optimization problems, you'll remember from the day 1 lesson, which was on perimeter and area, we had 2 metrics we were working with, so we made 2 equations. Today we're going to work with surface area and volume. So I'm going to start with surface area. And my surface area formula traditionally includes 2 sides that are width times height, 2 sides that are width times length, and then 2 sides that are length times height. But this does not have a top, so I am going to just manually create the formula. So we've got 1 base on the bottom, so that's width times width, so that's W squared. And then this area on the side is width times height. This area on this side is also width times height. The one in the front is width times height, and so is the one in the back. So all 4 sides have the area width times height. So I'm going to write my surface area as width squared plus 4WH. And then I know that my surface area is 108 square inches, so I'm going to drop that in over here. And now I have an equation relating width to height. All right, next up, they're having us find the dimensions that produce a box with the maximum volume. So next up, I'm going to create a volume formula. And volume is traditionally written using and calculated using length times width times height. But in this case, our length is the same as the width. So we have width times height. So I'm going to substitute length with the width. And I'll just clean that up a little bit and call that W squared H. And they're having me find the maximum volume. Now you'll recall from our prior unit, we know how to maximize functions or find maximums on a function by finding where the derivative is equal to 0 or where the derivative doesn't exist. So we're going to have to start by finding the derivative, but this function actually has 3 variables. So I don't want to differentiate this with 3 variables. I would prefer to write volume in terms of one of these letters. That's why we have this other equation over here. So I am going to use my surface area relationship to solve for a letter, and I'm going to choose to solve for H because there's only one of them. So I'm going to solve for H. I'm going to subtract my W squared and then divide both sides by 4H. I'm sorry, by 4W. So that leaves me with 108 minus W squared over 4W, and that is equal to H. This expression down here is now an equivalent expression to H. So I am going to substitute it in place of H in my volume formula. So that is W squared times 108 minus W squared all over 4W. And what I've now done is write volume in terms of just one letter, which is going to be a lot easier to differentiate. If we had 3 variables, you'll remember from related rates, we wind up with lots of more intricate differentiating that we have to do. We'd have to use the product rule. Sometimes we wind up using the chain rule when you have multiple variables. But in this case, we want to simplify this as much as possible with just one letter. When I differentiate this, I don't want to use the product rule here, so I'm going to distribute my W squared. So we'll have 108 W squared minus W to the 4th all over 4W. I don't want to use the quotient rule either. And since there's just a single term on the bottom, I'm going to divide all of my terms in my numerator by 4w. So 108w squared divided by 4w, 108 divided by 4 is 27. W squared over w is w. And then I'm going to have minus 1/4. W to the 4th divided by w is w cubed. All right, so now I have a nice, simple volume formula, writing volume in terms of width. And now I am going to differentiate this function. So derivative of 27w is 27. I'm using my power rule here, so minus 3 times 1/4 is 3/4 w squared. And now I've got my derivative. I want to set my derivative equal to 0. So I'm going to move up here. And I'm going to set this equal to 0. And solve for w. And so I'm going to move my 27 over. I need to either divide by negative 3/4, or I am going to multiply both sides by negative 4/3. And on this side, 3 goes into 27 9 times, so I have 36. On this side, my coefficient cancels, and I'm left with w squared. And then we'll take the square root of both sides, and I am left with plus or minus 6. All right, so with optimization problems, you want to use some logic here. And our w represents the width of this rectangle. A width of a real life figure cannot be negative. So I'm going to throw my negative out, and I only care about the 6. But if you forgot to do that, either way, once we find the point where our derivative is equal to 0, we haven't confirmed whether it's actually the maximum yet, and that's what I'm looking for. So even if you had started to lay both of our critical values on a number line, we're going to test those numbers out, and we're looking for where our derivative changes from being positive to negative. We know that's what would make a maximum. And this is a good point also to talk about domain of this problem. So our input is represented by width. And not only can the width not be negative 6, but it really can't be anything that's negative, or it can't be 0. So I'm actually going to cap this at 0, and I'm going to cross off the rest of this. We don't even care about anything to the left of 0 on our number line. And I'm going to substitute numbers in between 0 and 6 and 6 and infinity to find out what the sign of our derivative is. So you can substitute 1, and you can actually substitute 0 in if you want, because it's not a critical value, but I'll substitute 1 in. So if we substitute 1 on up here, 1 squared is 1, times 3/4 is 3/4, 27 minus 3/4 is definitely positive. If I plug in 7, okay, that's a weird number, so why don't you just plug in 1,000. 1,000 squared times 3/4 is going to be way larger than 27, so that's going to be a negative number. And that does confirm that we do have a function that is increasing and then decreasing, so we do in fact have a maximum at width is equal to 6. So I've got one of my dimensions. I have the other dimension also because those are both widths, but I do need to find height, and you'll recall we have a formula over here for height, so I am going to substitute 6 into my height formula. And that gives us 108 minus 36 all over 24. And that is 108 minus 36 is going to be, my bad, that's going to be 72 over 24, which is going to be equivalent to 3. So we have a height of 3, we have a width of 6. So I'm going to come over here, and our final set of dimensions that produce the maximum volume would be 6, and we're in inches, by 6 inches by 3 inches. And you'll recall both of our widths are 6, our height is equivalent to 3. Now there is actually a second part to the question, which is what is the maximum volume? So this is really like part A. Part B, to find the maximum volume, if you just had the width, you could substitute your width into your volume formula. But in this case, we already found all three dimensions. So I'm just going to multiply those out because that's length times width times height. So 6 times 6 times 3. So that would be 36 times 3, which would be 108. And this is a volume measurement, so that would be inches cubed. Okay, so that is our day 2 optimization example. I do have one more example for this lesson, but I will record that in a separate little video. Okay, good luck to you guys. Bye-bye.